Thank you very much for the introduction. I am Paul Debevec from Google Research and the USC Institute for Creative Technologies, and it's a pleasure to be giving one of the keynotes here at the International Symposium on Mixed and Augmented Reality. The title of my talk is on shining light between real and virtual worlds, and it will touch on things involving mixed reality, augmented reality, and also virtual reality. And I thought what I'd start out with is a technique for virtual reality for creating 6 degrees of freedom video for watching virtual reality video. And this is a project that I was very happy to get to work on at Google that began with the idea of trying to record all of the rays of light that come into a spherical volume, maybe 1 meter in diameter, so that with the magic of light field rendering, you'd be able to show something to somebody in a VR headset that wouldn't just have all of the information you need to look around, but also to generate novel points of view in the scene, depending on how you might move to the left or to the right or forward and back or even up and down within the scene. Currently, a lot of virtual reality video only works by producing a left panorama and a right panorama so that you can look around and get stereo as long as you keep your head straight and look at the horizon. But as soon as you look up or down or tilt your head or try to shift left and right, the viewpoints don't match up to what your brain would be expecting them to do. And the technique that we have by recording with a wider array of cameras arranged in a sphere and using our form of light field rendering produces a better result. These are some of the colleagues I got to work on this project with, and here's one of the scenes that we recorded with our light field video technique. Normally, this would only produce a left eye view and a right eye view that you could see in a VR headset. But from these synthetic renderings we've created, you can hopefully see that we have produced 6 degrees of freedom where we can actually freely move the viewpoint left and right and up and down after the fact. We can pause the scene at any time and then actually show that we're able to change the viewpoint around. For example, this light stand here in front of Alexa Mead, one of our artists in residence, actually clearly moves left and right in front of her. And there's pretty good edges that you can see here. There aren't like stretched polygons that you see around there. And even things like volumetric stuff, like the smoke and the fire that you saw earlier, things like specular reflections, like you can see here in the sand and the reflections of the man and his dog as you move back and forth, are reproduced pretty faithfully. And we were able to do that, again, using our variants that we have of light field rendering. We were particularly happy with the fur from this fluffy dog that you can see here, and some results moving around in the cave. So this is what it would look like if you had a VR headset on. You can basically move around anywhere as long as you are standing without moving your feet too much, or sitting down in a chair without rolling around too much, everywhere you can lean around into, and change the point of view. And the algorithms actually can run in a web browser. The camera that you see here is what we call the Sentinel Rig. It has 46 of these Yi 4K action sports cameras. The whole thing cost about $6,000 to make. It's all on a $200 acrylic hemisphere and some 3D printed brackets, and there's some synchronization cables that make them work together. And they record 46 video streams of relatively synchronized wide field of view, 120 by 90 degree field of view video. And then the goal of our DeepView algorithm, which uses machine learning, is to transform this scene from 46 video streams into RGBA alpha layers. These are spherical shells, each of which has red, green, blue, and alpha channels, so they can be partially transparent. And we start with about 100 of these layers, but then our algorithm turns it into about 16 layers, each of which has its own depth map, which allows us to compress this and put our data into a texture atlas so that we can actually compress and stream the data. So it's trained with lots of data of examples of if the original cameras here look like the scene looks like this, then the in-between views look like they should be something in between. And here is the texture atlas, and here it is playing back. Every second or so it re-atlases itself, and it doesn't create too much temporal instability. And this produces video that you can actually freely move the viewpoint around within about this 1 meter volume, which is pretty good for virtual reality. So I can certainly talk about it and show you some examples in video, but what's far better is if you would like to go to our website, which you can see right here. There is a number of in-browser demos where you can move the viewpoint around, and there is a downloadable virtual reality demo that you can run in headset, free to download, that will let you see about 3 minutes of light field video content in your own headset with 6 degrees of freedom. So it'll work on an Oculus Rift or a Vive or a Windows mixed reality system. We hope you'll have a chance to check that out. So that's one aspect of lighting, was the light fields, but here we're using the light that we're capturing basically to generate novel viewpoints within a volume for more comfortable virtual reality. And another thing that historically I've gotten to be involved in, which is a use of capturing light, is a process called image-based lighting. And this is something that's used in visual effects, where you want to insert new objects into a scene but light them the way that they would have looked if they were actually there. Obviously, this has got applications in augmented reality as well. And back in the late 90s, I directed a couple of short animations that recorded light from the UC Berkeley Eucalyptus Grove and St. Peter's Basilica to illuminate synthetic objects that I inserted into this scene. The lighting was recorded as panoramic high dynamic range images, either by tiling a panorama or using fisheye lenses or taking pictures of a mirror ball in exposure bracketed series and then unwrapping it and assembling that together. There's some downloadable LightProbe images you can play with on our LightProbe website. And I mentioned it has something to do also with things you might like to happen in augmented reality. A lot of AR applications are inserting synthetic objects into the scene. And wouldn't it be nice if the kinds of objects that you're putting out there could look just as realistic as if professional Hollywood visual effects supervisors had gone out and recorded the illumination, and you're illuminating that light, those objects or those characters, with the light that was actually there to give much more realistic integration. Well, we can't send out a visual effects crew all the time for your augmented reality application. All we really have is your cell phone. And with just a cell phone, the lighting data that's coming in is pretty much coming in off of the video feed, off of the back camera. This is a far cry from a high dynamic range panorama. It's certainly not panoramic. It's actually only about 7% of the sphere of directions of lighting that could be coming in on a typical lens. And it's not high dynamic range, obviously. It's just a single exposure. And so places where the light would really be coming from, even if they were in the field of view, would be clipped. And as an example, these are two synthetic objects, one's lit with low dynamic range lighting, one's with the full high dynamic range lighting effect. And you can see there's quite a difference between the two. So we had to have some way of magically inferring the high dynamic range panoramic illumination that you would get just by seeing the video feed of the background image in your cell phone. And to do that, we developed an algorithm that we call the deep light algorithm. And this was a Legendre et al. CVPR paper last year. And to do this, we got a lot of training data and, surprise, we trained a machine learning algorithm to figure out, or at least imagine, what the lighting should most plausibly be for all of the scenes that you might see in your cell phone. And the training data that we went out and collected was built with a couple of these rigs that you see. It's a cell phone aimed at a couple of reflective spheres. One of them's diffuse, one of them's mirror, one of them's kind of halfway in between. We call it a matte silver reflection. And these spheres, just a low dynamic range image, because they have different material properties that are taking different convolutions of the incident light, you can actually back out what the high dynamic range illumination effects would be from them. And since we just press record on the thing and then run around the scene, we get all of this, kind of self-documenting data of this is what the background looks like, and then this is what the spheres actually in that scene would look like. We have to crop the spheres out afterwards, but this allows us to then get a lot of data of if the background looks like this, then the spheres look like this. And so this is some of the training data that we got going around, lots of interior environments. Google offices were a major piece of this here. We did go both indoors and outdoors. And the network basically has all of these examples of if the background looks like this, the lighting should be this. So then, if you put in a new background and you don't tell it the lighting, you can have it figure out what the lighting most likely is. And in fact, there's even some generative adversarial networks that try to make up some of the data plausibly for the higher frequency details that might not really be observable in that environment. So we actually got this to run in real time on a cell phone, and it is now part of the ARCore augmented reality package that you get on Android phones. And the feature is called Environmental HDR. So if you're writing an augmented reality application, then you are able to call it up, get your lighting returned to you in a couple of different forms that hopefully one of them is useful for how you want to light your objects. And these are some actual results of taking this rocket that has both diffuse and specular material properties and placing it relatively realistically into a number of scenes that we've got on our cell phone backgrounds. And here's a few more results that we've got. So we were very happy to be able to take some image-based lighting technology, some machine learning technology, and ship it in an actual product that people are using as they develop AR applications. This made us wonder, since sometimes in the image there's pictures of a person, is there an even better job that we could do in estimating lighting if we know that there's a picture of a person in the scene? And we asked ourselves, could we in fact use a face as a light probe image? And that's some recent work that we've done, Legendre et al., that will be presented very soon at SIGGRAPH Asia 2020, which is an algorithm we call face light that goes from an image of a face to an estimate of what the lighting is like with a light probe. And this is also something that we trained with a lot of data and made a machine learning network to do. The data set that we got is that we recruited over 70 people, range of ages, genders, different skin tones. We had people wear different clothing and make different facial expressions. And each one of these people, we would bring into a special light stage device, the newest light stage device that we've built over at Google in our office in Playa Vista, which has about a 3.5 meter sphere of lights and cameras. We ran 6 of the cameras so that we got 6 viewpoints for each subject for all the lighting conditions we'd record. Mostly frontal, a little bit of variation. We're kind of optimizing for selfies that you might take, where the face is mostly toward the camera. And then for each person's expression and whatever they were wearing or however they were accessorized or what expression they were, we would record very rapidly many different lighting directions. There's actually 331 different lights on the stage. We'd run them one at a time, and then we would be able to do post-effect image-based relighting. I can show you that in a second, but these are 24 of those images. You can see they're from behind, from the front, above, and below. And then using some techniques from our very first light stage paper back at UC Berkeley at SIGGRAPH 2000, we know that if we have a face lit from every direction that light can come from, and we have a high dynamic range light probe image that tells you the color and intensity of light, you can basically multiply all of the images of the face by the colors of the illumination from the corresponding directions, sum them all together, and that produces a relit version of that face under that illumination. Even if there's different colors and different intensities coming from different directions than what you actually recorded in the light stage. So this allows us to create training data of faces composited onto backgrounds. We actually recorded an alpha channel as well for faces by lighting up the background behind people. Synthetically, which are pretty realistic data of this is what this face would look like in this background illuminated by the light of that scene. And of course, we already had this data from the Deep Light project of lots of backgrounds and lots of lighting conditions. So each one of these faces shows an example of what we're going to train our network with. It's a face where we happen to know the ground truth illumination because we've synthesized that face under the lighting of one of these illumination environments. And our network, pretty basic, we want to be able to then, since we've trained it with lots of examples, this is what the face looks like, this is what the lighting should be. Now we give it an image of a face. We don't tell it the lighting because we don't know, and it will predict the illumination. And then we can create a loss term to train it so that if we do know the real illumination, we try to minimize the difference. And there's a little bit of generative adversarial networks as well to estimate the higher frequency components. So taking a look here, let's take a look at some results of the algorithm. So these are 2 input images, and the estimated lighting that the network came up from those images. And if you look at the diffuse sphere, the matte silver sphere, and the mirror sphere, they seem hopefully reasonably plausible for what the lighting would be. But we can validate this a bit better by, for example, applying this lighting, using image-based relighting, to another face that was not in the training data set, but we did have light stage scans of, or this one light at a time data. And you can see here, these are faces that were captured in light stage, not used for training, illuminated by those lighting estimates. And hopefully it looks similar, like these two faces are lit by the same light. Now notice that these two people on the top row have a different skin tone. And we were concerned that the algorithm might tend to estimate less light for people with darker skin tones and more light for people with lighter skin tones, because the pixel values are either lower or higher, which could be explained as an illumination effect, but it's actually an effect of the reflectance, of the unknown reflectance of the face. And we're actually very happy that we were able to check that the algorithm is largely robust to being able to estimate illumination, the same kind of lighting regardless of what the skin tone of the person is that's being observed. So it really did do something kind of smart for that. If we take a look at what these folks actually would have looked like literally under the same light that the test subjects here on the input were, you'll notice that it's very consistent. So the algorithm really does seem to be able to pull the lighting off of a face in a way that it can realistically illuminate a different face with it. And as another comparison, we said, well, do we really need to estimate the full light probe image with all these different lighting directions? What if we just do the first 9 spherical harmonics, like a lot of lighting takes place? And you know, it matches the spherical harmonic lighting reasonably well, but you can notice if you look closely that our full HDRI maps that we pull off of the face actually reproduce specular reflections and shadows quite a bit better. The faces look quite diffuse under the second order spherical harmonics. So there's a couple more results. Here's a video result of one of our co-authors, Jay Bush here. She's holding a reference sphere just to kind of validate this, and then we're running the algorithm on her face every single frame. This is the lighting that it gets. She's walking in and out of shadow. You can see the algorithm is pretty temporally consistent, and generally speaking, the matte silver ball estimate here is pretty consistent with the matte silver ball that she's holding. As another example, we took this kind of photo that's just kind of a random photo we found, and we estimated the lighting off of it, and we asked, can we use this to illuminate a digital human character? So this is a digital human character that happens to be breathtakingly photoreally modeled, made by Ian Spriggs. And we rendered that character with that background under that lighting, and it's pretty consistent. So that's a sign that we got the lighting accurate enough to be useful. And then finally, here's another result where we pulled lighting off of very different illumination. This is more shadowy than sunlit, a different skin tone, a different kind of background, and it still is able to illuminate this digital human character consistently with the lighting that we pulled off of that. And one last example, these are two examples where augmented reality objects are being placed into the background, and they are being illuminated by light that's being estimated off of the face. And you can use that as a test of, hopefully, consistency. These are specular objects, so it's actually looking at a diffuse face and estimating specular HDRI environments, or reflections of a full HDRI environment, which is a bit of a trick. And also, it's relatively temporally consistent. You can see that the lighting maybe changes on the SIGGRAPH balloons in the background a little bit over the sequence, but overall, it's pretty believable and consistent. So we were happy, definitely happy with that result. So another thing that we've done over the years, and on the theme of the talk of kind of shining light between real and virtual worlds, this is a way of kind of pulling lighting off of real people's faces. What if we wanted to put lighting back onto people's faces? What if we wanted to illuminate a person with a high dynamic range image-based lighting environment? That's something we got interested in doing almost 20 years ago for our SIGGRAPH 2002 paper, a lighting reproduction approach to live action compositing. And we built this device. It was light stage number 3, which was 156 RGB controllable light sources arranged in a sphere around the subject. And what we could do is take our high dynamic range image-based lighting maps, sample them down to those 156 lights, trying not to alias anything, light the person with the light of one of our light probes, and then composite them into a background plate from that light probe image. And that's what you're seeing on the right side are our friends Emily and Alana that are being illuminated by the light of the Eucalyptus Grove, the Uffizi Gallery, Grace Cathedral, and composited in. And over the years, we had a chance to actually use this on some collaborations with the motion picture industry. We illuminated actors in costume for Spider-Man 3 using HDRI environments. We also helped do some face replacement work for the movie The Social Network, where Armie Hammer, who had a dual role and wasn't always playing both of the characters at the same time, needed to be illuminated in post-production with the lighting that was recorded on set, so that the face replacements that we recorded on these red cameras would actually be lit the right way, so when they'd composite over it would look realistic. Both of those are just trying to illuminate head and torso, but what we had thought of, even back to SIGGRAPH 2002, is that it'd be great to build a production studio out of this technology, to actually be able to illuminate an entire set with image-based lighting so that you can composite actors into all sorts of scenes and have it look realistic. Something that we've been very happy to do more recently is to actually build one of these large-scale image-based lighting systems for one of our collaborators in China called Sous-V, a visual effects company that ordered an 8-meter diameter light stage from our laboratory that has about 1,200 lights on it. And you can see it's got a light up floor. It's got a little area for the actors to act in, and they have some green screen behind. And when I got to visit a couple years ago, they had a demo where they have this scene of a couple of Chinese actors talking to each other. It's sort of an intense scene that they've got. And they will invite you to sit in a chair. They'll use the system to reproduce the lighting of that scene that had already been shot, and then they will edit you into the scene as if you were actually one of those actors. So this is me about ready to learn what I'm supposed to do to go into the scene, and I don't have time to show you the whole sequence, but I'll show you kind of the results where there's me composited into that scene, lit by the reproduction of the light, and then there's the actual actors who are lit by that light, and it matches pretty well. As it turns out, they use this system quite a lot when they need to add actors into a scene who weren't there at the original time of filming. And this happens sometimes where they need to change the actor in a show or add a new actor to the show for entire seasons of a television show or for an entire motion picture. And using this technique where they can instantly change the lighting from one illumination condition to the next over and over, they're able to produce realistic results of compositing much faster than you could with traditional production techniques. In fact, they can do 80 to 100 shots a day with this technique. It was really nice to be part of this because it had been, at the time, a while since we'd worked with industry on an image-based lighting project. And the previous time had been when we worked with Alfonso Cuarón and Emmanuel Lubezki to help develop the technology for doing lighting reproduction for the movie Gravity. And here you can see Alfonso Cuarón directing some test actors, the actors who would eventually be Sandra Bullock and George Clooney, in one of the light stage systems. This is the light stage at Light Stage LLC. And we're playing back illumination conditions to try to create photorealistic composites in scenes. And based on these tests, they actually decided to use this kind of technology surrounding actors by LEDs, and they used LED panels surrounding the actors in a 10-foot by 10-foot by 10-foot cube called their light box to illuminate Sandra Bullock's face and George Clooney's face, sometimes even head and upper body, to composite them into these space scenes of floating through the International Space Station or spinning out of control into space with all of the bounce light from the Earth and the sun and whatever you'd have from the interiors, which was very realistically done. And at this point, everything has converged that, in fact, people are building these kinds of lighting reproduction stages all over the place to do what they call now virtual production as one of its key components. Films like Asura from China, First Man, the TV shows Westworld, and The Mandalorian are all using stages built from LED panels to illuminate their actors for more realistic composites and quicker production. One of the issues, of course, though, is that now, whether you're using individual lights or LED panels, you're really only lighting people with red, green, and blue LEDs, which is not the best color rendition that you can get, because simulating the spectrum of daylight or tungsten is something that's very hard for these kind of little spikes of red and green and blue spectrum to do. RGB LEDs, like you can see on the left, tend to light people very differently than full spectrum light sources, as you can see on the right. And so we've done a little bit of work at USC ICT to build lighting reproduction systems with actually 6 channels of illumination: red, green, blue, cyan, amber, and white, in order to reproduce illumination, so that if you know what your HDRI map should be, but you also know what color charts look like in the scene, which tell you a lot about color rendition, you can accurately reproduce illumination quite realistically between how a subject lit in the light stage would look and how the subject would look in the real world without having to do any kind of color correction. So here, the subjects on the left are actually lit by real illumination outside our institute. We recorded the light with spheres and color charts and then played that back in the light stage, and their reproduced appearance composited into those backgrounds is on the right. And without any tweaking of the color balance, they match quite well, which we were happy about. We're able to take this technology even a little bit further, where you might think, wouldn't it be great if you could record your actors in a way that you could change the viewpoint after the fact, maybe kind of like a light field, and change the illumination on them after the fact. And using the light stage at Google, which has not only about 100 cameras around it in the 331 lights, but also a number of high-resolution depth sensors, we got to work with the augmented perception team on developing a high-resolution volumetric capture system that uses time-multiplexed illumination, 2 lighting conditions that bounce back and forth, you can see them here, at 60 frames per second, that give us an image of not just the RGB color of the actor at every point, but also their surface normal and a measure of their gloss map as well, their specular roughness at every single texel. With the high-resolution depth sensors that were custom engineered for the project, we get millimeter, maybe even sub-millimeter resolution in combination with the surface normal maps. And we can then change the viewpoint and the illumination to composite real actors lit by the light of virtual sets or lit by the light of real scenes. And here we had special hardware and special active lighting conditions to do it. We knew there would also be interest in potentially relighting just a single portrait. Suppose you take a picture on your cell phone and you decide, wouldn't it be nice if the lighting were better in this way or this way? And using some deep learning algorithms and some of that same kind of light stage data that you saw that lets us simulate how a given face would look in any possible lighting condition, we're able to train a network that sees a face in one lighting condition and can imagine what that face would look like in a different lighting condition. And that's a paper that we had last year at SIGGRAPH called Single Image Portrait Relighting, a collaboration with UCSD. And I'm happy to say that with some inspiration from this paper, a bit of re-engineering and such, this kind of effect is now available in the latest Pixel phones that are coming out from Google, which is known as its portrait light feature. So if you actually take a selfie image, you can then virtually move a virtual light source around to relight or augment the lighting in your photograph after you've recorded it, which is a kind of magical thing. And it does a pretty good job. It even simulates kind of the combination of diffuse and specular reflections, some of the shadowing information, and it works on a variety of skin tones as well, which is very important. So I hope you have a chance to try out some of these algorithms. I'm looking forward to answering a few questions if you can think of any of them. I'd like to thank some of the many collaborators that I've had on these projects here. This is actually just a small sampling, a couple of contact information down there. And with that, I'll turn it back over to our organizers. Thank you very much.